So I have my headphones on. So may you just warn me when, tell me when we are ready so that I can start. Okay.
Okay.
Thank you.
I think we are ready now. Hello?
Yes, I'm there. I was muted.
Okay.
Okay, so we can start. So I will continue with the discussion today about symmetrization and anti-symmetrization, and I will introduce something which is called second quantization. Now, second quantization is a new formalism that you will use in the next semester in many cases, and I have no, so I mean, just to derive it, it will take too long, too much. So I'm not going to derive it. I will try to give you some idea why such a thing is, such a formalism is useful and what does it mean. And I will tell you the rules or how the rules apply. So if some of you is interested in just going through the derivation, then I can pass some material and then we can discuss. Now, let me stress the fact that what you are going to learn in second quantization is nothing else that a kind of generalization. Oops, I don't know what I did. Sorry, I was just pressing with my finger, but sorry. Huh? Okay. It's the generalization of what you know about A, the operators A and A dagger that you learn in the harmonic oscillator. Okay. But you will see that introducing creation and destruction operators is very useful in handling many particle system. And I will, again, I stress you, I will give you the rules, but I will not tell you how to derive it from the beginning. Okay, so this is a bit complicated for this course, and it will take too far away. So what did we discuss yesterday? Yesterday we discussed many particle system, many particles, and we saw that in quantum mechanics, when you deal with identical particles, then it is a must to end up with a description which takes into account the fact that the wave function should have some symmetry under the exchange of particles. Okay. So if I have a function of, so I just write it as a wave function, okay? R1, R2, Rn, then the question was, what is the relation between this and the wave function where I exchange, for instance, the first two, okay? Indices. So what is the relation? Then what we found that the only possibility, there is a relation, and the only possibilities are that under exchange of these indices 1 and 2, so I'm just writing just the wave function, but yesterday we saw that this discussion applies. So for instance, if I take just using the Bra-Ket notation, if I exchange the index, so the I and the K, so these are alphas, okay, written badly. So then we saw that the property of the wave function should be either even or odd under the exchange, under this type of exchange. So far, I'm considering situation in which we have non-interacting particles. When I write this, I'm considering non-interacting particles, okay? But we saw that this parity under exchange is valid in general. We just studied a simple example of two particles interacting through some two-body potential, and also there we saw that the wave function should be also eigenstates. The eigenstates of the Hamiltonian should be also the eigenstates of the this P operator. Okay. Now, sorry, just a moment. Just give me 1 second. Now, this led us to two classes of particles, fermions and bosons. So fermions are antisymmetric. So I have wave function which are antisymmetric with respect of this exchange, while bosons are symmetric. Now, do you have questions so far? I'm just recapping what we discussed so far. Okay. Now, we saw that if you have, let's say, particles with let's say if alpha 1 and alpha n are the quantum numbers contained in this particular wave function that we are considering, writing down such a state does not obey this property. On the other side, we saw that the proper symmetrized or anti-symmetrized state is the one in which we sum overall possible permutations in which we consider a superposition of these permuted states, okay, alpha p1, alpha pn, with a factor which is either +1 or -1. Okay, +1 is for bosons, -1 is for fermions. Do you have questions on this, or can I go on? Okay. Now we saw, so you, and again, you can endeavor. Oh, good. No. So I mean, I don't. I think it's the same. Okay, but it's just I'm exchanging two indices. Okay, but the only thing I'm saying is just permutation, and in the colloquial language of physicists, you talk about exchanging two particles. I'm answering to the question that is in the chat. Okay. Now, did you try to write down the wave function I told you with 3 particles? Hello? Okay, I have 1 yes. Did you try or not? So please answer, because it is impossible to proceed if I don't understand what you did or you did not do. Okay, so for me it's fine if you say no, but I should know. If you simply did not try or simply you did not succeed. So please let me know.
Is it the
Yes,
exercise or?
Sorry?
Is it the exercise or the part where you expand the?
No, with the exercise I gave you with 3 particles.
Oh, well, I just followed the one that you wrote, but not the exercise. So I mean,
it's fine. I mean, you don't have to justify. I just to know. I mean, look. It's not that I can talk to a wall, to a digital wall. I'm talking to human beings, so I need to have some feedback. Okay, so that's why I'm asking questions. It's not that I'm just checking and say that you're good guys or bad guys. Don't worry. Okay. Now, there are now 2 concepts that I need to introduce that allow me to go to this idea of second quantization. So these are conceptual things. So there are no formulas to write, but or I can write a formula, but please tell me if this is clear or not. Now, let me consider just two particles, okay, to make the discussion simple, but it is straightforward to generalize to many particles. Now, let's suppose that you have two particles. I want to consider the case of bosons, simplicity, but really it does not matter. Okay, so let's consider the wave function of two bosons, which are in state A and state B. So I have psi A of 1, psi B of 2. These are coordinates, okay? Then I get plus psi A of 2, psi B of 1. You agree that this is the right symmetrized form, okay? And I want to consider another example, another situation, which is phi 1 and 2 is equal to the case in which I have psi A of 1, psi A of 2. Okay, so I'm considering two cases, this case and this case. Now, do you agree that the second case, this one, is automatically symmetrized, right? Say yes or say no.
Yes, yes.
Okay. Now, the fact that you are considering, sorry, that you are forced to consider symmetrized wave function leads you to the fact that actually the only thing, so in order to describe this wave function, so for the first case, it is enough that I tell you, look, there are two particles, one in state A and the other is in state B. I don't need, because I cannot tell you that which one is where. And for the second case, I just tell you, look, there are two particles in state A. Would you agree that this, I mean, suppose that you already know a basis of single particle state, which are these psi A, psi B, psi C or something. So if you want an example, a specific example, just imagine that you have a square potential, and then you start putting many particles in this square potential. So to start with, these particles do not interact. For some magic that we are not interested in, they do not interact. Okay? So, and I prepare a given eigenstate of many particles. In this case of two particles. Okay? Now, A and B are just the different n, because in a square potential with infinite walls, these are so n labels, the index n labels the state. Okay? So if I put two particles in this state here, if I tell you I'm putting two particles, one in state A and the other in state B, do you agree that you are automatically able to write down the wave function? This is a question, so you should answer.
I think so.
Okay. I want to hear from the others.
Yes.
Okay.
As they are bosons, so it's just like psi 1, 2.
Yes,
Right?
but the same discussion is true for the fermions. We'll see the fermions in a second.
Yes, yes.
Okay. So you see that if, so just imagine that I should, I mean, I mean, if you do not have this anti-symmetrization or symmetrization, then I'm supposed to tell you, you have to put the first particle in the state A and the second particle in the state B, okay? Because this is what I should tell you. But now, since the state, the physical state, should be symmetrized, then specifying this is wrong, So the only thing you need to know is that there is the number of particles which are present in a given state. Okay? So in the second case, this is exactly what happened. I just tell you, look, there are two particles in the state A. Okay? So you see that once you know the single particle state, then automatically the wave function is defined by just saying how many particles there are in each of the states. Are you with me? So for instance, if I give you let's consider the case of bosons with 3 states, sorry. Okay, let's consider this. I call it psi 3. So I have 1, 2, and 3. And I tell you that there are 2 particles in the state. So there are 2 particles in the state A and 1 particle in the state B. Okay? Then automatically you know how to write the wave function. So you have to start psi A of R1, psi A of R2, psi B of R3, and then you start symmetrizing. Okay, there is a 1 over square root of 6 of normalization. Then you have psi, plus. And then, for instance, you exchange 1 and 2, nothing changes. But let's write it. So you have psi A over 2, psi A over 1, psi B of R3 plus, okay? Then you have psi A of R1, psi A of R3, psi B of R2. And then you continue this way, okay? And you find all the 6 combinations. Then you see, for instance, that these 2 get a factor 2, right? But also here, the only information I gave you is there are 2 particles in the state A and 1 particle in the state B. Fine? Now you see,
Yeah, it's
yeah.
fine.
Okay, so you see that just you should start thinking that if I have a way to implementing the symmetrization automatically, then I can label the states rather than writing down all possible wave function and with this symmetrized form. Just imagine this is, you have already 6 terms for 3 particles. Just imagine in a solid you have 10 to the 23 electrons of this kind, and it becomes practically impossible to write down the wave function describing the electrons in a solid. Okay, so actually what you really want to do is to find a way of labeling the state which is much more economical, in the sense that it should capture the relevant information. And from the examples I gave you today, essentially the relevant information is how many particles are present in a given state. So you start with a single particle basis, okay? Just keep this example of the square well, and then you have a set of quantum numbers. Then you use this as a basis to describe the many particle state, and that's it. The only thing you need to do, and I repeat it again, is just to specify how many particles are present in a given state. Now, if you have to deal with fermions, the only possibilities are that in each state you have either 0 or 1, because Pauli principle forbids you to have more than one particle in a given with a given set of quantum numbers, okay, with all the quantum numbers being the same. If you have to deal with bosons, then you may have in each site how many particles you want. Okay, so just keep in this mind, because yes.
I have a question. This case is not valid in case of fermions, right? To get psi A, psi A.
No, this case. No, this case is only valid for bosons, because for fermions, okay, sorry, I just made a mess. For fermions, you have Pauli principle, okay? So you just see it from here. If you would put here a minus sign, when A is equal to B, you get this minus the same, and you get the 0, okay? So for instance, let's do this example. So just imagine that you have our example with the square well, okay? Let's see if you like this. I mean, you did not like my drawing for the berry face. So
Sir, I want to ask something.
Go ahead.
For two particles in the same state, then the total wave function is only the product of individual wave function or not?
Yes.
That we have written in second equation.
Yes. So you have that if you have two bosons, because you see, if just let's see here. If A's, I mean, if the A's are equal, essentially you have only one. Okay. You have one. I mean, this is automatically symmetric. This is the question, right?
Yeah.
Okay.
Okay.
What is wrong with this? Tell me.
Actually, I want to ask for two particles, say 1 and 2, if they are in the same state,
Yes.
then their total wave function is the product of individual wave function or not?
In this case, yes. Not always. I will come to this in a minute. In this case, yes.
Means for bosons only, or for fermion also?
So for fermions, it is forbidden, because you cannot have two particles being with the same quantum numbers.
Yeah.
So when you have two particles with the same quantum numbers, we are discussing essentially only about bosons, not fermions. And but this is not the whole story, and I will tell you in a minute. So that's why I don't want to finish the answer. Okay, just wait 1 minute.
Okay, thank you.
And I will finish. But for this example, yes, you're right. This is just a product, because you can verify this by just applying P to this wave function, and then you verify that this is an eigenstate of P. Okay. Now, So I just consider my square well, and I have my label, okay? Something like this, okay? So this is n equal 1, n equal 2, n equal 3, n equal 4, and so on and so forth. If I tell you, suppose that we have 4 particles, okay? So let's consider the case of 4 particles. Now, if I ask you, so let's consider again bosons because it's simple, okay? So how many terms should enter in the linear combination of the symmetrized wave function? So how many permutations you have to consider?
24.
24. So you see that if I ask you write down the wave function, if I give you this exercise, you will hate me, because if you have to write the wave function 1, 2, 3, 4, this will contain 24 terms, okay? Some of them may be equal, but essentially you have 24 terms, okay? But then on the other side, I can tell you, look, I have these 4 particles, and I put one example. I put two particles in the state 1, and 2 particles in the state 4. Okay, so you see this automatically fix the 24 terms. But if I tell you in words, then this is much simpler. Then the question is, good, probably there is a way, a different way of that labels the states, which automatically consider only symmetrized states, and then only the only information I have to give is to give you the number of particles in each state. In particular, here I should tell you 2002, which tell you 2 particles in state 1, 0 particle in state 2, 0 particle in state 3, and 2 particles in state 4. Okay? Hello?
Sorry.
Yes.
What do you want to do again by assigning the number of particles?
No, I don't want to. I mean, what I want to do is something which will come in a second. What I want to tell you is that, so I want to be sure that you agree that considering symmetrized wave function, you don't need to specify particle 1 is here, particle 2 is there. The only thing you have to say for those examples that they are making, how many particles are in given single particle states. If this is okay for you, this is the only thing I want to tell you so far. I really want that this is the information you are getting. Okay, so
Professor.
yes, no, yes, so there
yeah.
are various questions. So there is a question, I still didn't get what? And then I come to you, okay? So you have to say what you did not get. Okay, so so you don't have any mic, so you cannot talk, right? So there is, I still didn't get what you want to talk about. Now, then it's very difficult to answer. What I want to talk about is the fact that I want to label states So, okay, so let me ask the question. I have 6 particles, okay, which are, I give you the exercise, 6 particles, in which 3 particles in 1 particles in 2, 1 particles in 3, and 1 particle in 4, okay? Are you able to write down the wave function?
Sorry, can you repeat?
Yes. So let me consider the example with 6 particles, okay? So this example here. I have 6 particles, and I tell you, I have 6 particles in which I put 3 particles in n equal 1, 1 particle in n equal 2, 1 particle in n equal 3, and 1 particle in n equal 4. Okay?
Yes, yes, I guess we can.
John, I will answer one by one. So first, answer to my question. Are you able to write down the thing?
I guess.
Yes, but do you agree that it gets extremely complicated because you have to consider
Yes,
6 factorial states?
Yeah,
Okay,
it's quite long.
so just imagine that you want to describe electrons in a solid. So you have 10 to whatever number. Okay, can you write down a wave function? No, this is impossible. Okay, so writing down wave function properly symmetrized is something which does not work. Now I answered our questions. Okay, sorry. Then what I want to tell you is that there are different ways to describe the states which automatically implement symmetrization or anti-symmetrization. And for doing this, the first thing you have to understand is that when you have a symmetrized wave function, since particles do not have anymore an identity, okay, they are indistinguishable, then the only information you have to provide is telling how many particles are present in a given state. Okay, now there is another question that if you, I mean, the number of combination is always n factorials, but in the case of, if you have, so not all the terms are different, okay? So in the wave function, then some of the amplitude will enter with a factor 2, 3, 4, and so on and so forth, okay? This is what I, okay. So when, okay, so the other question I don't understand when you say labeling the particles. What I mean is, I'm not, so what we discussed yesterday is that we are not able to label particles because particles cannot be identified. If this is what you asked for. Okay. So what I want to do is find another way, let's not call it labeling, it's another way to characterizing the states, the state. And I'm trying to convey the information that in this case, since symmetrization is a must and you have to do it anyhow, it is already enough that I tell you how many particles occupy certain states. So I pause for a second and I want to know if this is now clear or is still not clear or is still unclear.
Professor,
Yes.
the example you're giving us here, the n equals 1 have three particles, is for bosons only, right?
Yes.
I mean, yeah.
Yeah. For fermions does not work.
Yeah. So, I mean, when you're supposed to have 6 factorial term, it can be reduced to like several terms.
Sure, but if you have 10 to 23 factorial, look, you may reduce it for sure, but it will be a large number. Okay, so don't worry. So I think labeling particles is distributing them in the states we have. Yeah, yes. If for you labeling particles is like this, yes, I just say that, so, but I cannot label a single particle. I cannot say particle 1. This does not make any sense. I can only say there are 3 particles in the state n equal 1, but I don't know which of them among the 6. Okay, this is important.
So so the number of particles in each state.
Yes.
You can say.
Yes. But I cannot say. So you see that when you, so let's say hoping next year we go in the class, then I can say Evan is on the first row and somebody else is in the second row and things like this. Okay, because I can just label the particles. Okay, now I'm labeling the state, saying it's like instead of if you were all twins. Okay, just imagine that there are I have a class of all twins, and these twins are quantum. I can only say there are 3 persons in the first row, 2 persons in the second row, nobody in the third row, and other people in the fourth row. That's it. Okay, this is what I'm trying to explain.
So, Professor.
Yes.
So your aim of putting a certain number of particles in a state is all about what? Is it about reducing the number of ways to reach the wave function or something else? I don't know.
So yes, I want to lead to a new description of a new formalism that describe wave functions, which is suited for many particles. So the formalism that we are using now works for 1, 2 particles, but even if you go to more complex situation, then it might be that it does not work very well. Okay, but I need to explain few things.
So is this like by explaining this you're trying to argue with us that second quantization is a good approach or something?
Yes.
Later?
Yes, this is exactly what I want to tell you, that the second quantization is the approach to make use of all this. Okay, now let's assume that this part is clear. Okay, let's go directly to the second quantization. Okay. Now, as I said at the beginning, now the second quantization is a way to take into account automatically symmetrization. And the idea is a generalization of what you already know for an harmonic oscillator. Okay, so let's start from the state alpha 1, alpha n. Okay, now So this alpha, so the alphas can be equal, okay? So for instance, if you have alpha 1, alpha 2, in principle, the indices can be, the quantum number can be equal if you have bosons, if you have fermions. No. So second quantization is based on the fact that you introduce the same, say, creation operators as you learn in the harmonic oscillator. So you just introduce a creation operator A dagger alpha, okay, such that when you start from the vacuum state, so you have 0 everywhere, and you apply A dagger alpha 1, A dagger alpha n, this is equal to alpha 1 alpha n. Okay, so it's nothing else that what I mean. If we consider, so these are exactly the same type of operators that you learn in the harmonic oscillators, but let's say here we are just introducing, saying if I have a state in which I have just the various quantum numbers of the n particles, okay, then I can create the state. So just to specify, in the example I gave you before, okay, so if I have 3 particles in one, I have 1, 1, 1. Sorry, no, I just write it differently. Okay, so I just write n equal 1. N is not nice because I'm going to use n for different. So let me slightly change the notation. I just call it p, okay, the integer, because this is symbol. Okay, I just call it p. It is an integer, but n, then here it will enter in this way. So I have p equal 1, p equal 1, p equal 1, p equal 2, p equal 3, p equal 4. Okay. So no, symmetrized states does not mean that they have the same quantum number. Symmetrized state means that you should be an eigenstate of exchange operator P. Okay. So you see, this is alpha 1, this is alpha 2, this is alpha 3, alpha 4, alpha 5, and alpha 6. Okay. So alpha 1 is the quantum number 1, alpha 2 is quantum number 2, and so on and so forth. Okay. So I introduce boson, I introduce creation operators that go from the state in which the empty state, I just go to the state alpha 1, alpha n. Now, for what we discussed so far, then I'm considering again the state alpha 3, alpha n. So the state alpha 2, alpha 1, alpha 3, alpha n should be either equal to plus minus the other. Okay, because the state should be symmetric. Now, in the case of the state alpha I had to write this permutation, all these possible permutation. Here, the only thing I have to require is that this state here is such that a dagger 1, a dagger 2, in 0 should be equal to to plus minus a dagger 2, a dagger 1, and everything else 0. Do you agree with this?
No.
Why not?
It's not. So you consider a dagger times the 0 state is the state, and then you apply the permutation.
Mm-hmm.
No, I'm asking because you just
sorry, you are
tell me
asking.
a
Okay.
dagger 2.
No. Okay. So sorry. Sorry. Now let's. Okay. So probably this is. Let me do it this way.
I see.
So let's call it this symmetrized or anti-symmetrized. I put SA. Okay. So it's not the single state. Okay. The symmetrized. Okay. So what I want to do is just that the symmetrized form should be the same. Okay. So this means that when I apply these operators in this order should be plus minus the same as the other operator applied with the reverse order. Okay.
Yes.
Okay. So this means that a dagger 1, a dagger 2 should be operators such that you have plus minus a dagger, there is no a dagger 2, a dagger 1. And the plus is for bosons and the minus is for fermions. This means that this translates with the fact that a dagger, let's say alpha, a dagger beta, I just call it alpha and beta 2 indices, for bosons should commute. Okay, so this operator should commute because there is a plus sign. So this means
Professor,
yes.
Actually, I'm a bit confused because why suddenly your states become a single state, like 0 only? Is it?
Okay, I just repeat again. Okay. I just use a slight different notation as in the notes. Okay. So I have alpha 1, alpha n, and this is, when I say symmetrized, can be symmetrized or anti-symmetrized. Okay, it depends if they are bosons or fermions. Now I introduce operators with the following properties. I dagger apply to the vacuum state to 0 to something empty should be alpha alpha. This is the rule. Okay. So it's like with harmonic oscillator. I have no particles. I apply an operator and the state will contain a particle in with quantum numbers alpha. Fine?
Yes.
Now, if I have many particles, then the state that I have to consider is a dagger alpha 1, alpha 2, a dagger alpha n applied to 0. Let's say this is a 0, a string of 0 should be equal to alpha 1, alpha n symmetric. When I write this symmetric, is this 1 over square root of n sum over p psi to the p, okay? Now, but then we know that when I exchange two particles, the state should be either plus or minus, right?
Professor,
I do not
why
hear you.
is it only for the symmetric one and not the antisymmetric?
No, I'm just saying I call it symmetric to say
I
that it should be symmetrized. Can be symmetrized, anti-symmetrized. If this confuses you, I put
see.
okay?
And is why is it only like 0 cat 1 1 1 0? Why don't you
Because
put like
I was
0 0
yes,
0 0?
because I said it. I was lazy. I don't want to write all the zeros, so it should be 0 0
I see.
0 0. Okay, I just put 0. Okay,
Okay.
I think 0. Okay, now we know that if I exchange, for instance, 1 and 2, then this state here is plus minus the initial state, right? So this means that A dagger alpha 1, A dagger alpha 2, if I consider first two indices, should be equal to plus minus A dagger alpha 2, A dagger alpha 1. Right?
Yes.
So this means that A dagger alpha 1, A dagger, oh, just write it here, sorry, just to be quick. This means that this is minus plus equals 0, where this minus is for bosons and plus is for fermions. So for bosons, the A dagger alpha 1, A dagger alpha 2, they should commute. For fermions, it's plus. This is called anti-commutation, I think you know. So A dagger alpha 1, A dagger alpha 2, they should commute. Clear now? Hello?
Yeah.
So is it clear now?
Yes. Yeah.
Now I want to hear the others.
Yes.
Yes.
Now,
Yes.
what did you, what of course, 1 and 2 are just two labels, right? So we can consider in general that this is, so we just consider alpha and beta. Okay. So alpha and beta, beta alpha leads to just commutation relation or anti-commutation relation, okay? Alpha, beta. Now, you see that if you use, I mean, we are not there, okay? But if you use these creation operators, then by having a precise requirement for the commutators or anti-commutators, then the states are automatically symmetrized or anti-symmetrized. Now, here at this level, you have to write down all the possible combinations. So here, the only thing you have to do is just to specify the commutation relations of the creation operators. Now, please ask questions. Hello? Is this okay? Do you also need the permutation of the creation operators? Yes. So this applies in general. So if you apply this commutation relations or anti-commutation relations, automatically you have the same. So let me make one example. So for instance, you have, just imagine the following: alpha 1, alpha 2, alpha 3 to 0. This is 0, 0, 0. Okay, then you see that basically this has the property that if you change any of them, because you can move, you can so this is equal to alpha 2, a dagger alpha 1, a dagger alpha 3, 0, 0, 0. So you have all the rules. I mean, so this applies to any permutation. You end up with the correct symmetrization or anti-symmetrization. Now, it is important to define the adjoint of the creation operators. So you have a dagger of alpha, and you take the dagger, okay? And we call it this A alpha. So,
Sorry, Professor?
yes, yes.
I think Lian means that we still have many permutations to do.
Sorry?
I mean, we still have many permutations to do, but now creation operator. So we didn't
Yes,
reduce
but
the calculation.
right. Now, this, you are going too far, too fast, because after 5 minutes of second quantization, then it's difficult to appreciate. The only thing that is enough that you, oh, no. So, I mean, it's still not shorter than the usual way. Yes, it is much shorter, but I cannot show it now. You have to see when you do the calculations, okay? And it's much shorter because you are going to write the state, which is automatically symmetrized. Meaning that, so the next step that we have to do is to learn how to write down operators in the second quantized form, and how to manipulate and study the dynamics and things like that. And then you will see that it's much simpler. Okay, so I can assure it's much simpler. But so far, you have to accept it. Okay, but anyhow, the only thing I'm just saying this, that of course, perhaps I understand. So of course, it's not that the number of permutation is reduced, because the number of permutation is there. What becomes much easier is to do calculations. Okay. Now, it is important. So sorry, let me ask the following. I think that this lecture will not, I will not be able to finish the second quantization. Now, I would like to ask you, are you okay in just continuing on Thursday at 11? Okay,
Yes.
so so I will write Patrizia that we will have also the lectures on Thursday 17. Okay.
But not at 11 because we have a course at 11. Maybe at 9.
9, I cannot. So we can do it Friday. Friday.
No, what I mean 11 is empty, right? The one that's filled already is 9, because 9 we have statistical mechanics.
No, it's 11 statistical mechanics. We can check the schedule.
I
Okay.
I just checked the email. I mean,
No,
No, no, you check the schedule. It's at 11.
okay, just a second. Is it okay Friday at 11? Also Friday, sorry.
Yes.
well,
Okay.
but the last email said it's 9. We should clarify this somehow.
Okay, let's do the following. I can do, so for me, 9 is not possible. So let me say the following. Can you check with careful when you can have a lecture? So I'm available Thursday, Friday, or Monday at 11. Okay. So you just check and you send me the email. Okay. Yeah, you check and you tell me. There is no reason to discuss now. You have to
Well,
check.
I mean, by the email they send
Just a
us.
moment. I
It's
mean,
9.
let's not waste time. So you just check it this afternoon. I'm just saying that it's fine for me. Thursday at 11, Friday at 11, Monday at 11, or Tuesday at 11. Let's do it anyhow before the vacation. Okay. So please check it and send it to send me an email. Okay. So I want to introduce this object. So the adjoint of sorry, stop with the chat. I forbid you to continue discussing with the chat because you have to talk to me, listen to me. Okay. You are going to sort it out. Don't worry. I mean, there is no point in discussing now. So you can discuss at lunch. So you will enjoy a nice discussion about time scale schedules for lunch. Now, I need so this is not enough. I need to have some extra information, and for that, I need to introduce this other operator that you know already, but this is here we are not having any harmonic oscillator. Okay. And so if I have a wave function psi, I would like to understand what is the action of the operator A alpha. Okay. Now, for doing this, what you have to do is just to look at some scalar product between A alpha. Sorry, I just am writing in a bad way. A alpha psi. Okay, this is the right thing. Now, if you use the just if you apply to the bra instead of to the cat, since we know that this operator alpha is the adjoint of a dagger, you should have this property. Okay. Now, it turns out that this means that also the A alpha and A beta should commute for bosons and anti-commute for fermions.
Sorry, I didn't get what you.
Yeah. Just a moment. I just write it and then I come back. So what I want to learn is, so I want to introduce a new operator which is this operator A. So that you know is called distraction operator, but for the moment we are not using any harmonic oscillator. Okay. And let's do it this way. Let's start. I just introduced, I would like to see the action between, so the action of the adjoint of a dagger. Okay. So I want to understand what does A, the adjoint of A to psi. Okay. So you know that basically you can use the properties that if you, let's say, if I call it, let's say, this psi A. Okay. Now, if I consider two states and I have the scalar product of psi A, this is also equal to phi A dagger. So instead of applying the operator to the ket, you apply to the bra, and then you have psi. Okay. I'm just using the standard properties of applying an operator. So if you apply an operator to the bra or to the ket, then you have to consider their median. Okay, their adjoint. Sorry, this is what I'm saying. So this means that basically to see what are the commutation rules of the operator A, the only thing I have to do is just to use the fact that these are the same commutation. Okay. Okay, let's do it again. Let me see. How can I? So is this relation clear to you? This is what I say. If you have two states, psi, and you have the state A applied to phi, okay? Then this is equal. So just tell me if, and then you apply to phi. Is this clear or no? So these are properties of operators. I mean, you can put any operator, say a dagger or something. Okay. This is the property.
Yes.
Okay. So for instance, if you apply an operator to the ket, if you want to consider the same, so that you have to consider the adjoint that applies to the bra. That is what I want to say. Now, if you use this property and use this exchange of particles, then you end up with the fact that also the distraction operators, so these operators, obey the commutation relations for bosons and the anti-commutation relations for Fermions. Okay. Now, exercise. So you have to do some exercise. So let's see, so that you learn. Now, trying to use these properties of the operators, try to show that if you have the state, so you have to show that this A is the distraction operator. So what it does is the following. Okay, before the exercise. Sorry. What it does is the following. So if you have the state alpha 1, alpha n, for this, if you apply a of alpha 1, this is equal to nothing, alpha 2, so there's nothing. So alpha 2, alpha n. So it just reduced the number of particles in the state alpha 1. So this is called distraction operator. Oh, I just already above. Okay.
So it's not 0. I mean,
no, it is 0 only if, for instance, this is an important point. It is 0. So in this particular case that I consider is non-zero because I just considered the case in which there was a particle in alpha 1. It is 0 if there is no particle. So if you apply the distraction operator on 0, then you get 0. Okay. So it just eliminate the, if there is a particle, it just eliminate the particle. If there is no particle, then it's 0.
oh, I mean, become state 0, like the initial state again.
So no.
Oh, okay.
I just repeat it again. So let's consider this case here. Okay. So I apply the distraction operator of the state related to the state alpha 1. Okay. Now, if alpha 1 is occupied, then the state disappears. The particle disappears. So there is nothing. So you have alpha 2, alpha n. Okay. Is it clear now or not?
I thought that was raising operator now.
No, this is A. The raising operators is A dagger.
I mean, when you move to 2.
No, sorry. Let's do the following. Let's consider the case in which I have, so alpha 1 is p equal 1, okay? Alpha 2 is p equal 1. The example I gave before with the square root, p equal 3. Then I have p equal, I forgot, 6. No, 4. P equal 5 and p equal 6. This is the state, okay, symmetrized. So sorry, I don't want to consider symmetrized. This is the state, okay. Now, if I apply A of p equal 1 to this state, then what happens is that I will have p equal 1, p, there was, this is 1, p equal 1, p equal 4, p equal 5, p equals 6. So you see one particle disappear from the state with p equal 1. Okay. So this state has 5 particles. This state has 6 particles. Hello? Is it clear now or not?
Yeah.
Okay. Now, I think it's already time, so let's stop here, because then I need to explain you commutation relation between A and A dagger, but I have the feeling that we need to digest a little bit of the story. So I will start again next lecture. Now, can you write me this afternoon or tomorrow morning at most, at the latest, so that we fix another lecture? Okay. So I need a volunteer that writes me on behalf of all the class. So who is going to write me? Hello? I need a volunteer. Come on, you have to send an email. This is something easy. Who's going to write me? Jonah? Okay, Jonah was volunteered by somebody else. Very good. So Jonah, just write me today or tomorrow, okay? Once you agree with everybody, and then we fix. Please remember that Thursday, Friday, or Monday, also Tuesday, but it is important that it's at 11, okay? Okay, have a nice...
Sorry, Professor.
Yes.
Can we fix another time to correct the exercises? I mean the one of square one.
Yes. Just fix. I mean, please, just if you can select, if you find twice, 2 times to, I mean, in this time slots, then it's fine. We can do it twice. Okay.
Thank you.
Okay. So Jonah, you tell me about exercise and. Okay, but for the exercise, let's do the following. I need, so how many exercises we had to correct?
I think it's more than 10. I don't know.
10.
No.
Okay, so
not all of them.
okay, so let's
Because
do the following.
already several lectures pass and you always give exercise. Almost.
Yeah, that's good. Now
Four.
you have to do the following. Since I forgot what exercise I gave you, let's do the following. I want to, so just prepare yourself a presentation for the exercise, okay? And then we correct them, okay? So you just prepare slides or whatever, so you show it in a decent way, so you share the screen. We can do it, I think one lecture is not enough, so we need 2 lectures. But it's fine, whenever you want to discuss, it's fine. But you organize yourself, and if you solve an exercise, just send me a program or who is going to discuss about which exercise, and then we organize these presentations, okay? And then I will follow and tell you what is correct and what is not correct.
Okay.
Okay. So Jonah, will you take care about all this as well? Please say yes. Very good. So have a nice lunch and see you soon. Okay, probably we need 2 or more lectures. Bye-bye.
Bye-bye.
Bye.
Scusami, non sono arrivato a prendere il telefono. Uh-huh. Uh-huh.